Hello, everyone. My name is Ben. I'm a research scientist at Together AI. At Together AI, our mission is to um, serve language models efficiently in order to democratize intelligence. So today we'll be talking about the methodology that we've been developing in order to serve language models faster, more efficient, and more cost effectively. So first, we'll be going over research overviews. There are a bunch of research directions that we have started at Together. First topic is on model compression or activation sparsity. Second topic is architecture adaptation. There are multiple architecture variants that we can do to adapt and make language models more efficient. The third topic is speculative decoding. It's a technique that boosts inference efficiency without affecting any quality. And the fourth topic is on post-training as a way to improve quality and improve quality efficiency trade-off for language models. Then we'll go over to the turbo optimization suite. This is a industry-grade research that is already in production, so people can use methods like quantization, turbo and custom speculators, and also soon we'll release efficient RL endpoints so people can benefit from the most recent research that we've done. So for Turbo Research Overview, we do research in a broad area of efficiency. So the things that are most obvious and is something we should do is quantization and hardware co-design. For example, newer hardware supports FP8 quantization and FP4 quantization. So using these quantization strategies allow us to host larger models and also speed up the models when the kernels are available. And we can do calibrated quantization and also quantization-aware training. And for quantization, we've done research that allow us to quantize without sacrificing model quality while retaining the speed. And this is through the co-design with the kernels as well. Other research include model pruning. For example, we can reduce model size, change model architecture, or induce model sparsity that we'll talk about in a little bit. We can adapt model architecture to diffusion LM. We can adapt architecture from transformers to alternative architectures like Mamba or other subquadratic architecture. And in terms of post-training, we've been working on RL training recipe and distillation recipe in order to distill more knowledge to models so that smaller model size, we can get more higher quality. And over the course of this year, we've released Deep SWE that perform well on software engineering tasks. And we also have turbo data collection that we use to train these models and perform large model to small model distillation. So the first research paper we'll talk about is TEAL, Training-Free Activation Sparsity. In this work, we observed that language models are quite sparse in the activation space. So we can look at the first figure here where we show that most of the activations are quite concentrated near the center, in which case if we mask out some of the activations to be zero, we can is equivalent to it being sparse, and in that case, we don't have to load some of the weights when we do inference. And then we can get inference speed up. For example, on the right side here, we show the speed up where 50% 50% sparsity results in 40% latency reduction. And this is because for some of the channels, we can skip the weight loading at all. So during decoding, where it is memory bound, we only need to load some of the weights. And as a result, um, we can get speed up by only loading selected weights. And on the bottom right, we show quality. So we can see that for 25% sparsity, 40% sparsity, the quality drop is quite minimal. And also compared to other sparsity methods, our approach is very competitive in terms of retaining quality, as you can see here. Another work on architecture is ladder residual. So in this architecture, we propose a parallelism-aware architecture where this benefits significantly for hardware where compute is quite fast, but is bottlenecked by things like communication. So on the left side here, we show standard transformers versus ladder residual. For standard transformers here, we can see that attention block and MLP blocks are sequential, meaning that for MLP, we need to wait for attention to be computed. And then for the next attention, we need to wait for MLP to be computed in order to start. But for lateral residual, what we propose here is that we do not have to wait for the previous module. For example, for attention, we can take the computation from the previous attention directly, not the previous MLP. In which case, once that first attention is done, then we don't have to wait for MLP to be finished in order to start the next attention. And in this way, we can overlap the all reduce. So all reduce can happen all reduce can happen after each attention or after each MLP. So the all reduce that happens after attention can go in parallel with the MLP that follows. And this results in the overlap in communication and computation and saves the sequential dependency. So in this way, we show that we have a really good inference speed up on the right side here. And in terms of quality compared to standard transformers, ladder transformer and standard transformer are quite comparable. So this is one way to speed up inference through architecture design. And yeah, we have other work that we've been doing at Together in this direction as well. Another work is to adapt standard transformers architecture to Mamba architecture, which is a subquadratic architecture that performs really well on long context and also have very high inference efficiency for long context. So what we do here is propose a way to initialize and adapt the architecture in a very efficient way. So in the orange cells here, we show that we take the initialized weights from transformers and carry that over to the adapted member. And for other modules, we initialize from scratch. And in the paper, we outline the recipe for fast adaptation. And as a result, we can get increased throughput with similar quality as we show here in the Mambit, so in the hybrid Mamba and Llama architecture. We obtain very strong quality based on R, MMLU, and GSM 8K and other benchmarks. And we also show improved abilities on long context, for example, for needle in the haystack benchmark as a benchmark for retrieval ability. We can show that there's generalization in terms of extending the ability to um, retrieve tokens that are in the long context better than standard transformers that were trained on only 2000 context length. We're able to retrieve up to 36,000 token context length after adapting to hybrid member. This also speed up long context inference significantly as well. Another work is speculative decoding. Speculative decoding is very important, and we use speculative decoding a lot because it's a clean approach to speed up language models without sacrificing any quality. So in this scenario, we um, show the Medusa approach where there are different decoding heads, different decoding heads propose tokens, and in this scenario, we accept tokens that are proposed from different heads. So then, once we accept multiple tokens at a time, that's where we get the speed up. So on the right side here, we show speed up for different model size and for different approach, Medusa 1 and Medusa 2 in the and the baseline without Medusa. And we also show the speed up on different categories where we can get 4.5 times speed up to three times speed up. And our latest work is Atlas, which is short for Adaptive Learning Speculative System. So this work is a new paradigm in language model inference by building runtime learning accelerators. So in the diagram on the left here, we have Atlas, where it composes of the heavyweight static speculator that does not change frequently over time, and the lightweight adaptive speculator that keeps changing depending on the traffic. So when new language model traffic comes in, the adaptive speculator keeps adapting. And then once the adaptive speculator becomes more confident after it learns enough, the confidence aware controller performs the selection and selects more tokens from the adaptive speculator. And once we are able to accept more tokens, then we get increasing speed up. So on the right side here, we show that for baseline, which is no speculator, and then the another baseline, which is turbo speculator, like this is fully static. Um, Compared to these two baselines, we get speed improvement that increase over time. For DeepSeek v3.1, we can get speed up to 500 tokens per second on Blackwell, on NVIDIA Blackwell. And this is even higher than some of the specialized ASICs such as Grok. So based on this framework, we can achieve really high peak speed. Yeah. Um, in terms of post training, that's another way to improve efficiency as well. So here we show that for decoder, which is the model we release, um, it is pushing the boundary of the Pareto frontier of quality efficiency curve. So compared to other models like O3 Mini, R1 Distill, or O1, deep coder performs really well on tasks like live code bench, but is also much smaller in model size. Um, and this is through a lot of post-training recipe and also system optimization. We show one example here on the right where we optimize scheduling for post-training in order to make the training more efficient and therefore able to train these models faster. As we show here, for RL training, most of the bottleneck is on the samplers, is on the rollout. Um, one of our solutions is one-off pipelining, where we perform scheduling intelligently in order to avoid the bottleneck and that increase the system efficiency during training. So now we'll cover the turbo optimization suite, like the products that we have available through together. So for turbo, we have industry-leading speculative decoding, the turbo speculator that we've mentioned previously. As we show on the left side here, we can see that our turbo speculator um, has results in the speed that is exceeding standard speculator that's off the shelf significantly. For example, for DeepSeek, we show that we can get 370 tokens per second versus 300 tokens per second. This is based on MTP speculator that's off the shelf. So we have an in-house proprietary algorithm and training recipe that is enabling us to obtain industry grade and very high performance speculator. And this results in the fastest DeepSeek speed in the world based on NVIDIA Blackwell. Uh, and once we train speculators to be more customized, uh, we can get more and more speed up as well. As we can show here that the speed up is quite significant for the various domains. And then we also have Atlas that works on top of this, where we can increase the speed even further. It's more of a granular customization. So for our research here, for production grade research, we also um, co-design with many things that we do at Together. For example, on the hardware side, system side, as well as kernels. So this is kind of a co-design, and this is our strength because we look at inference efficiency in a full stack way. So collaborating with kernel team and system team in order to advance on the algorithm that are kernel aware and system aware that are able to take advantage of other innovations and compound the inference efficiency even further. Yeah. And this one, we show the scenario where we stack many things together. For example, from standard quantization, FP8 to FP4 quantization to turbo speculator and to adaptive learning speculator system or Atlas, we can see that the speed improves from 100 tokens per second to 500 tokens per second. And this is 5 times speed improvement without quality degradation. Uh, Other things that we will have soon, and this is a preview, is on the turbo rollout for RL training. So as we have alluded earlier, turbo rollout here is taking advantage of the Atlas optimization in order to improve um, the rollout efficiency. So for reinforcement learning, the decoding phase, the rollout and the interaction with environments, this takes a lot of time. So and it takes a lot of work to set things up correctly, kind of manually. So what we're doing here is offering an endpoint for RL inference so that people can do it through API. So the difference here is we specify that we want to do turbo rollout with Atlas. And once we specify this, we'll be able to upload the weights that we want to start RL training. And during the training loop here, we can do inference through Together API with the optimized rollout. And we also allow updating the weight so that we don't have to manually spin up and spin down instances where the different weight corresponds to different model. This is more of a smooth weight update. And this allows us to take advantage of the adaptive speculative system as well that adapts over time with the traffic. And overall, this results in significant speed up for RL training. So as we can see here, the acceptance rate is the speculative decoding acceptance rate, which correlates with um, inference speed during rollout. As we can see here, on the x-axis is the training steps where we start from low acceptance rate. In the beginning, this is the scenario where the speculator does not know a lot about the traffic. Um, then over time is able to learn and improve acceptance rate and increasing to 0.8. This is a very high acceptance rate that allow us to speed up. And the special thing here is that for different training steps, this is corresponding to different target model, different policies as well for RL training. So if we had used a static speculator, um, the speed up will actually most likely go down over time, which is not the scenario that we want. So with Atlas optimization, we're able to achieve increasing speed, increasing efficiency as we train the model. So next um, we'll talk about our customers. So we have many customers that trust Together and use our services. So as you can see here, many foundation model labs and AI native applications and in addition to that, public sector and large enterprises. And the turbo optimization suite here is used for many of our customers. The most popular one being speculative decoding and quantization. And we'll have the turbo rollout for RL training soon, which will expand the scope in terms of what we can do to help enterprise and AI native applications improve the inference efficiency. And yeah, we're a trusted um, platform for many of the foundation labs when models come out like Llama. Earlier this year, OpenAI model. We also partner with OpenAI or other labs like Mistral or DeepSeek in order to launch models on day one. And these optimizations that we do. Apply for the serverless model in addition to the custom models on top of the open source models as well. Yeah, so that summarized the turbo research and turbo optimization suite. Yeah, thank you. Thank you so much.